Morning, everyone. So yesterday we had a look at many different functional groups. Functional groups are specific attachments of atoms. They give the molecule very particular behaviors, and they actually help you categorize our organic chemicals into many different families. We learned how to do a lot of the naming. Sometimes the suffix would change. Sometimes we would have the branches. I just want to give you a quick practice of that. We will later on in this chapter take a look at some of the reactivities that each functional group has, why they react in that manner, but we'll just start off with the IUPAC naming. So just for a quick warm-up here, I want you to see if you can write the IUPAC name. Pretty much the naming that we've been learning is set out by IUPAC, right? So it already is going to be the IUPAC name, find the longest carbon chain, number it so the branches occur the smallest number possible. All that is rules set by IUPAC. So let's just draw a few molecules here. Let's do a HOC110, CCNH2, COH, and then a C. I'm going to condense one on you here, CH3, 3C. CH2, 5, CHO. We also do need to get some practice going the opposite as way. So if I go give you the word name, you should be able to draw the structure. Can you draw for me the following? 4 bromo, 3 chloro, pentane, nitrile. Okay. So I encourage you just to pause the video. You can try it out for yourself. Okay. Assuming you've done that, you can check your work with me here. First thing we want to do is we want to just identify the different groupings. Okay, so what we have is we have this C110OH. That's actually the carboxyl group. So we actually have a carboxylic acid functionality. So carboxyl. We have an NH2, which ends up putting us in the amine family, and the OH actually puts us in the alcohol family. All right. So of these three functionalities, actually all three behaviors will be present on this molecule. Different parts of the molecule will behave in different fashions based on which functional group there is. But in terms of the naming, one of them has to take the ending. One of them has to take the suffix. In this case here, carboxylic acids are probably the most important family. So this is actually going to take the suffix. This is actually going to change the really ending. That way we can see the alcohol group as a hydroxy group, and we're going to see the NH2 as an amino group. Carboxyl groups are always terminal, so we're going to count carbon 1, 2, 3, 4, 5. There's 5 carbons in a row, so it's going to be penta. The ending is going to be oic acid. And then we're going to say at position 4, there's a hydroxy. At position 3, there's an amino. A for amino actually comes first. So let's write this here. 3 amino, 4 hydroxy. Right. So that was for the amine group. That was for the alcohol group. And that's all branched off a pentanoic acid. This next one here, I'd encourage you just to draw it out. It's a little bit hard to read when it's sort of condensed like that. Anytime it's a CH3, it tells you it's a terminal group. So let me just sketch it out here. So I have CH3, I have another. Sometimes they even say H3C. They're just trying to hint at which side the hydrogens are on. Still a methyl group. All of those ones here are branched off this single carbon here. Then what we have is we have a bunch of CH2s. CH2s are more so those mid-chain ones. If I am holding carbons on either side of me, I only have 2 extra arms to hold hydrogen. So I have 5 of those. So 1, 2, 3, 4, 5. The rest I assume are saturated with hydrogens. Then comes the CHO group. This CHO group is a shorthand for an aldehyde group. That means we have a carbon, double bond O, single bond H. That one there is terminal. Okay. So once you draw it out here, it's not actually that bad. This is the terminal group. This is going to be position number 1. We want to find the longest carbon chain. Let's find out how many carbons I put together. 1, 2, 3, 4, 5, 6, 7, 8. At position 7, there's 2 methyl groups. Even though they're on the same position, you still want to say 7, 7 dimethyl. The dimethyl tells you there's 2 1-carbon branches somewhere. One's on 7, oh, the other's on 7 as well. And then off of a octane, we actually have a 8-carbon parent. And the ending for an aldehyde changes to Al, so octanol. No number for the aldehyde because that one there is terminal. Going the other way here, it's actually easier. I would start off with the suffix. I can say, okay, so we have 5 carbons. That's the pent. Pretty much everything is single bonded with the exception of this nitrile group. The nitrile functionality you need to recognize is a CN functionality. So let's start off one side with a C triple bond N. That's what a nitrile group is. We have 5 carbons in a row. So 1, 2, 3, 4, 5. Remember, the parent is just made out of the carbon, including the carbon in the nitrile grouping there. And then all we're going to do is we're going to have numbered it. Position 1, 2, 3, 4, 5. At position 1, there's a chlorine group. At position 4, there's a bromine group. For my regular grade 11s, I still give them periodic table for this section, and because sometimes they just forget, oh, chlorine is Cl, not just C. Or bromine, it's not just B, it's Br, okay? So make sure you write the correct symbol here. Also note, because these are halogens here, they just have lone pairs on the end. If I had a methyl group from earlier, if I had one of these C groups, it was understood that the remaining are hydrogens. That was only for carbon, because carbon has the equivalent of 4 valence electrons. These chloro and the bromo groups here have nothing else attached to it. There are no other hydrogens. If I actually drew out the other hydrogens, there would be 3 hydrogens there. This one already has 3 attachments, so this has 1 more hydrogen, 1 more hydrogen, CH2. This is already triple bonded, so that's 1, 2, 3, 4. So there's no hydrogens on the end there. Right? So just make sure you get a lot of practice with naming these compounds here. For today's lesson, what we're going to switch over is we're going to start looking at different types of isomers. We're going to start off with the easier type of isomer today, called a structural isomer. But let's just talk in general here. This should be the next page over. Anytime you have this prefix here, iso, it means something is the same about them. Right? Isomers are going to be different compounds. They have possibly different physical characteristics, different reactivities. What's the same about them is they have the same molecular formula. They have the same number of atoms. It's just a matter of how they're actually bonded together that they actually are different. Okay, so some of these ones here are going to differ in chemical. Some of them are going to differ in physical characteristics. Today, we're going to mainly focus on the first type, which are called structural isomers. If I ask you for a definition of structural isomers, I do want you to reiterate, yes, what's the same about them? What's iso about them? They have the same molecular formula, but they have a different... you could totally say different structure, but I try not to define it with the word inside it. So we might say different bonding, different arrangement, something that has the notion that things are attached differently. Okay. Tomorrow's lesson here, we're going to come back and we're going to take a look at stereoisomerism. Whenever they say stereo, they're talking about the geometry. So in this case here, seems really restrictive. We're going to actually have the same molecular formula, so exactly the same number of every element. We're even going to have the same structure. Everything is attached in exactly the same ordering. I can't actually move things around as we'll see in this lesson here. But what's different about them, again, anytime you see this word stereo, they have a different spatial arrangement, a different 3D arrangement, and therefore they are different isomers of each other. Okay? Stereoisomers can be further divided into 2 further important classes. One's called the geometric isomer. The other is called an optical isomer. Geometric isomer, they're trying to phase out that language. Geometric isomer is now just specifically referred to as cis-trans isomerism, or they can call it EZ isomerism. We'll see this in tomorrow's lesson. Or optical isomers here. Optical isomers are later on going to be called RS isomers, and sometimes they're referred to as configurational isomers. Okay. So just starting to summarize for you the different types of isomers that we have. Both of these are actually configurational isomers, but they differ in the 3D arrangement. Right. We want to introduce a very important term at this point. As we start looking at different structures, specifically the carbons, or even nitrogen sometimes, we can refer to the carbons as primary, secondary, or tertiary. We can use symbols here, sort of first degree, second degree, third degree here. And I'm going to use this definition here. A primary carbon is going to be the carbon attached to the functional group. And because it's primary, it's functional group and at least 2 hydrogens. Usually exactly 2 hydrogens. Okay, so let's take a look at a molecule here. Let's do ethanol. Right, so ethanol is an alcohol functionality. As I start looking at sort of which carbons are primary and secondary and whatnot, I look at the carbon that has the functional groups, because that's usually going to be the reactive part in the molecule. More on this later on. This carbon, it's holding the functional group, it's holding the alcohol functionality, but you notice it's also holding 2 other hydrogens. So this carbon is referred to as a primary carbon, a first degree carbon. you will sometimes just sort of hint at, well, if I'm primary, I'm also usually going to hold one carbon. We're going to see that sort of comparison here for secondary. For secondary, very similar. For the carbon that has the functional group, the carbon is actually holding the functional group, the special grouping on the molecule, and only one hydrogen. Right. And if you actually count it up here, if I'm only holding one hydrogen, so let's say I'm methanol, so C with the OH, I'm only holding one hydrogen. That means I have to hold two other carbons, right? So again, just for ease here, focusing on this carbon, we can call this a secondary carbon, two with that circle there, because it's actually holding two carbon neighbors. At tertiary, you guessed it here, this is a carbon with the functional group, with the special grouping on the molecule, and it holds three alkyl groups, carbon with functional groups, and three. Anytime you have an alkyl branching, alkyl means a carbon branch. So if I have a tertiary carbon, a C, maybe holding, I've been using OH just for simplicity here, I may be holding sort of three chains. This chain can even be longer, maybe I put it on an R group, but definitely it's not a hydrogen. So therefore, this is the tertiary carbon because it's holding three carbon neighbors. So just one easy way for you to think about is a primary, secondary, tertiary. Look at how many other carbons is it holding on to. But I had to word it that way to make sure. Let's say I have a methane. Let's say I have CH4. First thing is there are no functionalities, right? Or even methanol if I wanted to. I can still refer to this as a primary because it's holding at least two hydrogens, even though it's not holding one carbon. So that's why I sort of went through this little detour and I actually gave you a little bit more of a restrictive definition. The type of isomer we're going to look at in today's lesson are referred to as structural isomers. These ones here physically require you to break bonds to actually convert from one form to the other. So before discussing these structural isomers here, let's recap. We saw this term here 2 days ago with homologous series. A homologous series are basically a family of molecules. Homologous series were chemicals that had the same general formula. For example, for an alkane, we had the general formula. Pretty much every carbon is holding twice the number of hydrogens, with the exception of the two terminal carbons, they hold two extra hydrogens, so 2n plus 2. The members, they differ by CH2 attachments. Remember, CH2 are these sort of middle attachments. I just steadily lengthen the chain. Some other things you can tell me here, because the functionality is going to depend on what sort of functional groups that I have. If I'm an alkane family, whether I'm a long chain alkane or short chain alkane, I all behave the same. So these ones here will have similar chemical reactivities because that depends on the functional group. But in terms of physical characteristics like boiling point here, as the chain itself starts getting longer, we're going to start getting stronger London forces and the boiling points are going to increase. We're going to get a sort of a gradient in physical properties. Right. So they give you an example here. Let's start off with methane. I'm going to start off drawing these skeletal structures. So methane is CH4. Right? Methane is a little hard to draw a skeletal structure because there's only one carbon. But once I have ethane, eth means 2, I can actually draw a skeletal structure just a line like this. And what that implies is if I don't tell you what's on the ends of these, you can assume that they're carbons. You can assume that they're fully saturated, so CH3, CH3. So that one there's an ethane. As this chain here steadily gets longer, let's say a propane, let's say a butane like that. Remember, it's implied every kink, every corner actually implies a carbon. As I steadily get longer, we have stronger London forces. So one example here, we might say stronger London forces. So therefore, one gradient is going to be higher melting point or higher boiling point. What about methanol and ethanol? Well, these ones here have the alcohol functionality. They have the special OH group. One thing is this allows for hydrogen bonding. This is a nice molecule where the one side actually does H bonding, but as the chain itself starts getting longer, let's say I have a long chain like that and then an OH group on the end, as this non-polar part actually starts getting longer and longer, that's actually going to give this whole molecule non-polar characteristics. So what we have is we have one side polar and one side non-polar. This ends up forming those bilayers for cell membranes, maybe micelles. Basically, we have the polar head is liking of other polar environments, but the non-polar tails are really scared. A lot of fatty acids are actually non-polar tails, non-polar chains. Okay, so make sure you know this definition here. This is what it takes to be a homologous series. As we start taking a look at structural isomers, right, we might still very well be in the same family. We had said they're isomers, or something is the same. They have the same molecular formula. They have the same number of every type of attachment, but they have, like we said earlier, a different structure, a different bonding, a different way of actually attaching. So what I want to show you here, for structural isomers, to convert one to the other, you physically need to break bonds. Okay. That's actually true for geometric isomers as well, but in a different fashion. So let's start off here with butane. Butane is the first thing that starts having isomers. Butane has 4 carbons in a row. 1, 2, 3, 4. It's in the alkane functionality, so everything's just single bonded. I'm assuming the rest of them are just bonded to hydrogen. Sometimes they even refer to this as N-butane. That N there is just shorthand for, oh yeah, all 4 carbons in the butane are in a straight chain. They're just sort of straight across, butane. Is there a way I can have the same formula? This one here would have 4 carbons and 10 hydrogens. Same formula, but a slightly different bonding. To make sure we don't miss out on any structural isomers, I usually start off with the longest one. So butane, let's put all 4 in a row. And then what I'm going to do is I'm going to slowly make the chain slightly shorter. So what this guy can do is I can actually have a 3-carbon chain. What if I physically break this bond? That would otherwise here would have a methyl group. Can I reattach the methyl group anywhere? So let's try it here. Then I would have a 3-carbon chain. Can I reattach the methyl group here on this ending here? Well, nope. IUPAC would still say, yep, you have 4 carbons in a row, it's still butane. That doesn't help. Can I reattach it on position number 3? Well, again, that's going to be a butane. So the only one place that's actually physically different from earlier, we can actually attach the methyl group here. Let me just make sure we have all the right number of hydrogens as well. This one still has 3 H's. 3 H's. This carbon that's holding 3 other carbons, so it's tertiary carbon. This one here has 1 extra hydrogen. Great. This also has the formula C4H10, but it's a molecule that's sort of compacted on itself. When we do the IUPAC name, I can't string all 4 carbons together. We're no longer butane. I can only string 3 carbons together. At position 2, there's a methyl group. So this is actually referred to as 2-methyl propane. So structural isomers here will have different names. As you start drawing them out, if you start naming them, anytime you end up with the same name, you found the same isomers. So these are 2 different isomers of butane. Notice they have exactly the same formula, but somehow the structure, somehow the way they're bonded and attached together are different. Evidently here, as the chain gets longer and as you start getting different substitutions, you're going to get many, many more isomers. So let's try it out here with pentane. So I want 5 carbons in a row. Let's go practice that sort of skeletal structure. Just many different ways of showing it. The sides there are carbons. It's assumed that the remaining are going to be hydrogens. So that's just going to be pentane. So you can call that N-pentane if you like. And then again, steadily what we're going to do is we're going to slowly chop off 1 methyl group at a time. So let's take a look at whether this pentane formula C5H12, let's take a look whether I can reattach this carbon somewhere. You cannot reattach this carbon here on any of the ends. Because if I reattach it here, that's just going to be a 5-carbon chain. I reattach it here, also going to be a 5-carbon chain. I could reattach it at position number 2. Again, let me just, as we're learning this here, I'm just going to show you where the carbons are. Usually I don't show what's in the red here. Now all we have is we have 4 carbons strung together. We're no longer a pentane. We're now going to be a butane. So something is different about the structure. You can actually count out the formulas. They're all single bonded anyway, so we're going to still be C5H10. This one here is going to be a butane, except at position 2, there is now a methyl group. So 2-methylbutane, that is a structural isomer of pentane. These are 2 different isomers of each other. Is it possible for me to have reattached that methyl group? Let's reattach it at position number 3. Right? Great, 3-methylbutane. Huh? Well, no. Based on our IUPAC naming here, once you find your longest parent, when you name your branches, you always keep the numbers tiny. So even though this is technically the 3rd carbon in, I would have actually counted it the other way. 1, 2. Oh, that would just be a 2-methylbutane again. So that's the same isomer. That's like this molecule having just sort of rotated, twisted itself. I'm looking at it upside down. So because that has the same name, that's not a new isomer. There is no 3-methylbutane. Okay. Are there any other isomers then? Well, we're doing this really systematically. I'm slowly chopping off sort of one methyl group at a time. I chopped off one. Let's see if we can chop off another one. So I have the equivalent of 2 methyl groups off of a propane. Again, you cannot add your branches onto the ends. Let me make that note here. We cannot add alkyl branches like methyl groups. We cannot add alkyl groups to the ends, or it just extends the parent. So remember, we had 5 carbons to play with. I'm now down to looking at a propane, 3 carbons. I have the equivalent of 2 other methyl groups. If I reattach them on the ends here, well, now I just have 5 carbons in a row again. I just have pentane again. So because it is a carbon branch, we are limited to having to put them somewhere mid-chain. They can't be on the ends. I can put them both as methyl groups on carbon number 2, right? That's a different isomer. That would have a different name. I now have a propane, 3 carbons in a row, 1, 2, 3. And at position 2, there are 2 other carbon branches. So this one here is called 2,2-dimethyl propane. Different name, different structural isomer. Totally different physical properties. If you're talking about London forces, although the total number of atoms are the same, the molecular mass is roughly the same, I would argue that a straight chain would typically have slightly stronger London forces than if I took these carbons and sort of balled it up here as a smaller structure here. There's not as much surface area exposed. I would probably expect this one here would have slightly weaker London forces. Okay. As I had the equivalent of 2 methyl groups, you could have thought of, well, why can't I attach it as an ethyl? Well, let's try our propyl again. So we have propane. We have the equivalent of 2 CH2 groups to reattach. I can reattach them as an ethyl. Have I actually created a new isomer? Well, let's just try it here. Well, I now have 4 carbons in a row. At position 2, there's a methyl group. I now have produced 2-methylbutane again. I already had that isomer, so this is not a new isomer. This 2-ethyl propane doesn't exist. That's actually 2-methylbutane. Okay, so really, really systematic. Just takes a little bit of practice for you to do this. So let's just keep going here. So we have hexane. Always start off with the longest one. So we have hexane. We have 6 carbons in a row. Just going to get you familiar with many different ways of writing it. That one there is called hexane. That is potentially your first isomer. Then slowly but surely, what you're going to do is you're going to slowly start chopping off some of these carbons here. I'm going to chop off the 1 carbon. Let's take a look at what the isomers can be if I actually have a 5 carbon chain left over. I cannot reattach the methyl on position 1 or 5, right? I can reattach on 2. So what's this guy called? This guy here would be called 2-methyl pentane. I can reattach on carbon number 3. Right. So if it has a different name, it's a different isomer. I haven't seen it yet. 3-methyl pentane. Can I reattach on carbon number 4? So let's go here. 1, 2, 3, 4, 5. If I try to reattach it here, what would you have called this one? Well, let's find the longest carbon chain. Well, that's 5 carbons long. Oh, this one here would have been called a 2-methyl pentane. I already had the isomer. So those are the only versions. This is a duplicate, so don't draw that one there. Let's do the next one. What sort of butanes can I have? So shorten the chain to 4. Now I have the equivalent of 2 carbons to play with. Again, because they are carbon, they are alkyl branches, you cannot put the carbons on the ends. So I could put both of them on carbon number 2. So this one here would actually be called 2,2-dimethyl, right? Different name, different structural isomers. You can also always verify for yourself that when you count the number of H's, that it's always the same. 2,2-dimethylbutane. What if we have, let's put 1 carbon on top, 1 carbon on the bottom. Actually, single bonds allow for free rotation. More on this tomorrow. It doesn't matter whether on top or bottom. These can twist, no problem. The more important thing for today is just looking at the name. So 2,3-dimethyl butane. Right, that's a different name. Right, the numbers are slightly different. It's a different isomer. So far, I have 5 isomers. Can it be 3,3? Can I have sort of a butane here, and then I put it on, what would otherwise have been position 3, position 3. But again, if I name this one here, no, I would have counted it 1, 2, 3, 4. That's why IUPAC is really clever. If you always keep the numbers tiny, this is actually just your 2, 2 again. It's exactly the same. Remember earlier, we could actually attach both carbons as an ethyl group. Let's see if that works. So I have 4 carbons here. What if I attach an ethyl group on this position? Is that a new isomer? Well, what's the longest carbon chain? The longest carbon chain here would be 5. On position 3, there's a methyl group. I already had the isomer there. Right? So you see, just really systematically, you're just trying to get a different way of attaching, a different way of bonding them together until we end up forming like a new molecule with a different name. Okay. Is it possible, just a guess, is it possible that I can have actually a propane isomer? So I would now have the equivalent of 3 methyls to put back on. They could be 1 ethyl and 1 methyl. Again, with the limitation, because I can't actually sub on alkyl groups on the ending, that would just extend the chain. I only really have the carbon in the middle. I can't attach all 3 methyls on the carbon. Carbon can't expand like that. So that means one side at least has to be an ethyl, one side at least has to be methyl. But even then, I would have now created a butane. This would have been 2,2 dimethyl butane, and we already had that earlier. If I try to make it a propane, let's attach all 3 carbons in a row. Again, we have a problem. This one here would actually be 5 carbons, and then we would have a 2-methyl pentane, and we have that there. So we would say there are 5 structural isomers for hexane. Obviously, as the molecule gets longer, we're going to have many more options. Okay. I'm going to leave example 4 for you to try here. What they're starting to do here is they're subbing on a bromine group. So imagine you have 4 carbons. You already have the equivalent of 2 bromines. You can look at all the possibilities of where you can put that bromine. You can put both bromines on 1, so it could be 1,1 dibromo. I would recommend to you do it really systematically. Move the bromine over, right? So I can have a 1,1, I'm not going to finish this one for you, but 1,1 dibromo butane. You can slowly move one of them, leave the other one alone. So 1, 2, 1, 3, 1, 4. Those ones there are definitely going to be isomers. Then move this group here. Then have the bromine at 2. What's 2, 1? Well, 2, 1 is just 1, 2, so that's going to be the same. I can have 2, 2, that's different. I can have 2, 3, that's different. What's the 2, 4? If a bromine was on 2 and the other one was on 4, this one was actually a 1, 3. You just want to avoid any duplicates. 3, 3 would basically be a 2, 2. And then again, maybe you can shorten the chain, make it propane, and then do this systematic work of finding where the bromines could be. As you look at this last one here, as you start attaching on O groups, this reminds you of the different functionalities here. You might actually end up having different functional groups here, all having the same behavior. For this one, let's just start off. We have 4 carbons. The alkane would have had C4H10 anyways, and all that we've done is for one of the hydrogens, we pulled off the hydrogen, and we subbed in an oxygen. What is the name of this functionality when it has an OH group? So this one here is actually an alcohol functionality, right? You can think of the alcohol as a branch here. This one here, the name, we have 4 carbons, so this is going to be butanol, right? I can move that alcohol group, so I actually want to specify, sometimes they put the number in front, 1 butanol or butane 1O. What if the alcohol group was actually sort of mid-chain? So what if it was like 1, 2, 3, 4, and then we actually have the OH at that second position? You can call it 2-butanol if you want. More conventionally here we say butane 2O, right? Both names are fine. Can I put it on position 3? Well, that would just be butane 2O. Again, you can shorten the chain. What if we only have 3 carbons left over? Then I have the equivalent of a methyl to play with and an alcohol group to play with. The methyl group is stuck to be just on the middle carbon because that can't be on the ends. It's going to extend the parent. And then the OH, we still have some flexibility. The OH can be on the side, can be moved in here. But physically here, we need to break the bond. If it has a different name, it's a different structural isomer. What I wanted to show you with this example here, maybe I'll do this in more detail tomorrow's lesson here, but there actually is another functional group here that also has single bonds that also have the same formula. Let's do C O like this. Instead of the O as sort of connected to an H, the O is actually coming in mid-chain. Hopefully you recognize from yesterday's lesson, this is actually an ether functionality. Right? So this guy here, again, it'll have a different name. The shorter group here takes the oxy, so methoxy. And then on position 1 on my propane group here, we have a propane, and then we would just put that 1 in front. So on position 1 on the propane, there's actually a methoxy grouping there. And again, you can play around. Well, where else can this oxygen group go? Could it be ethoxy? Could I shorten the chain? Could I put this C somewhere else? Pretty much, they all have to have the same formula, but something is physically different about the structure. So I'll leave those two for you to finish off. Example 4, example 5. There are a few more practice questions here for structural isomers. Okay, we'll pick it up from there tomorrow. Thanks, guys.